Brilliant. Well, firstly, thank you so much for the organizing committees for allowing me to speak about exoplanetary science. As Rob has shown, the vast information that one can gather from GALAH and other large spectroscopic surveys is incredible. And also, before I start my talk, I'd like to acknowledge the Gaiabal and Jayawa people, the land in which I'm standing upon today, and like to pay respects to their elders, both past, present, and emerging. So we are so tantalizingly close to answering one of humankind's grandest mysteries, and that is, are we alone? And we haven't yet been able to answer that question because it's a very, very complex one. But what we do know is that our solar system is indeed not alone, and that there are literally thousands of planets that have been discovered so far. At the moment, we have discovered way over 4,400 planets, and we know through exoplanetary statistics that that every star should have at least one planet orbiting around it. And so, with almost 100 billion stars within the Milky Way, there is plentiful of planet discoveries to be discovered. And with the likes of TESS and Kepler, there are now over 6,600 candidates waiting to be confirmed by ground-based surveys and follow-up surveys, such as Minerva Australis, which is both what Rob and I are a part of. And so just going back here, you can see that there are two main methods to find planets. Rob talked about the transit method, and there's also the radial velocity method. So with the transit method, you can get the radius of a planet, and then with the radial velocity measurements, you can get the mass of a planet. So with those observables and with models, along with the stellar parameters such as the effective temperature, surface gravity, your metallicity values, and in particular your alpha abundance. Alpha abundances are incredibly important for isochrone modeling of stellar mass and radii. And now with Gaia, with distances, you can obtain the luminosities, and combining all of that together, you can learn so much more about an exoplanet. So you can learn about its mass, its radius, its density through these elemental abundances. You can therefore determine the composition of these worlds, and with the period and the semi-major axis of these planets, you can therefore determine whether these planets are in the habitable zone. And from that, you can learn, if you know about the geological structure of the planet, if you're able to determine the atmospheric composition, which is something that we're still heading towards, and with the launch of JWST, which will, touch wood, hopefully launch later this year, getting atmospheric parameters from terrestrial worlds, we are getting closer and closer to answering that question, which I talked about earlier on. So this is an amazing slide here showcasing the four largest spectroscopic surveys that are currently running, the Lamos, Rave, Apogee, and Gala. And you can just see the overlap here between not only the surveys, but across the sky as well. And as Dennis and Rob had just mentioned, TESS is nearly an all-sky survey scouring the sky for exoplanets. And this slide here shows us the overlap. So all those points in gray are the other surveys that I just showed you. The purple points here are stars that have been observed by GALAH DR3. And you can also see these orange squares here are the cameras and also the sectors that have been observed with TESS. And what you'll notice is that you can see the Kepler, the K2 fields that Dennis and Rob just mentioned on the ecliptic there, and also this huge overlap down in the southern ecliptic here, and that's a part of the TESS Hermes survey. So GALAH DR3 is immensely important to the exoplanet community because not only does it include just general stars that have been observed by TESS in outside of the K2 and TESS continuous viewing zones, but also with those zones in mind of actually trying to find planets in those particular areas. So a part of my PhD, I've been trying to answer two Pretty interesting question. So one question I've been trying to answer is, what can we learn about current exoplanetary systems orbiting around GALAH stars? And the question that I'm going to lead on to start off with is, what can we learn about the types of planets that TESS will discover around GALAH stars? And so to do that, I combined the second data release, the effective temperature, the log G, the iron abundance, along with the alpha abundance to then get an overall metallicity and pop that into an isochrone modeling software package called isochrones, along with GAIA DR2 parallax and the magnitude values, your G band, your blue band, green band, blue band, and red band of GAIA, and also the 2 mass magnitude Z. And then combining that together, you can get the stellar mass, radius, luminosity, age, habitable zones, and abundances for the stars that are being observed with TESS. And so therefore, going down along those lines, I've created the GALAH TESS catalog. So we have 47,000 stars that have both physical and chemical properties, along with 4 key abundance ratios that are needed to determine the composition of the planets that will be found around these stars. So you can jump on to Data Central now, and this PDF will be available on Slack, and you can just click on the link there and they'll take you straight to the catalog. So what did we learn from obtaining the GALAH TESS catalog? Well, I've learned that the choice of stellar parameters matters a lot. And so what I wanted to do was that if you had an Earth-like world orbiting around these 47,000 stars, if you had an Earth-like planet that was both one Earth radii and one Earth mass, how different would it be, considering you would use, say, the stellar parameters from the TIC, the TESS input catalog? And so all of these single points here is what that Earth-sized and Earth mass world would actually be using those different stellar parameters. And you can see here, so these lines here just indicate what the likely composition would be for these particular worlds. And there's such a great diversity here in what would potentially just be a one Earth mass and one Earth radii planet. And so we need to have some sort of consistency in the stellar parameters if we're really going to say with certainty if a planet is the same size and same mass as with other surveys. Because if we go out and say, all right, we've discovered an Earth-like planet, and it turns out that it might be up here where it can just be some sort of water world where habitability might be plausible, but might be incredibly difficult compared to being somewhat an Earth-like world, then it's going to be challenging. And so, as I've just mentioned, stellar abundances can also help with the composition of the planets that they're likely to have orbit around them. And so you can see on the left-hand side here, I have a plot of the carbon to oxygen abundance ratio on the x-axis and the magnesium to silicon ratio on the y-axis. And so anything that's in orange here these stars would likely have exoplanets orbiting around them that would be geologically similar to those found within the solar system. And the stars in purple and gray would have planets that are compositionally diverse from the solar system. And so you can see here that about half the stars within the GALAH TESS survey would be like that of terrestrial planets that are found within the solar system. And there's other half that would be compositionally diverse from those found within our solar system. So it's really interesting to then work out the habitability of such worlds. And that is still an ongoing science question that's still yet to be determined. But however, these abundance ratios and just equating these abundance ratios from the stellar abundances to the planetary abundances might not necessarily be one-to-one as we're using in the exoplanetary community at the moment. And there might be more complex relationships, as Adebedikian has shown that there might be a slope. Plotnikov and Valencia have shown that there might be secondary processes that deviate away from these abundance ratios. And Wang has shown that you need to use some sort of devolatilization process in order to go from the stellar abundances to the planetary abundances. And this is just another plot within the paper showing how compositionally diverse these exoplanets might likely be. And to give you some sort of reference, thank you. Mercury would lie somewhere around here. And so now what I've done is, now with the third data release, I've looked at just the confirmed and candidate exoplanets that have been found both with TESS and with K2 and other surveys, and used GALAH DR3 stellar parameters along with GAIA EDR3 parallax values and magnitude values to sort of update the planetary parameters found within GALAH DR2. Now, a reminder that GALAH DR2 did not include the TESS Hermes survey, and nor did it include the K2 Hermes survey as well. So we have more exoplanets within GALAH DR3. And what I've done is, what's great about the NASA Exoplanet Archive now is that not only does it have just a single value for a particular exoplanetary system, but it has multiple. And so what you can do is you can use a weighted mean approach to get a more precise value on the fundamental parameters, such as your semi-major amplitude, on your radial velocity measurements, and also combine the change of flux measurements for your transit observations. And then so combining that with the stellar parameters that I've been able to obtain with GALAH DR3, I've been able to refine the mass and radius of some of these worlds to better than the mass precision of 8% and a radius measurement of 3%. So just to give you a quick summary, you can see here with Queensland 7b, one of the most studied exoplanets to date. This is the latest archival entry in orange here, and this is our updated value here. So that's showing us that Queensland 7b would likely have an atmosphere to account for its radius now, but considering it's over 2200 Kelvin, what type of atmosphere it'd likely have would be very, very interesting, and something that's well outside the scope of my research. But yeah, an interesting question nevertheless. And also, what's really interesting is that when they announced the discovery of TOI 1444b earlier this year, they noticed that ultrahot Neptunes, so ultrahot meaning that their orbital period is less than 1 day, tend to orbit around metal-rich stars compared to ultrahot terrestrial worlds. And so what I've been able to do is I've been able to use GALAH DR3 to actually show that that is the case. I mean, it is quite a small sample, but you can see here with the orange dots that the ultrahot Neptunes that I have in this survey do favor iron-rich stars compared to their terrestrial counterparts. And what's really interesting actually is that you don't find any types of these planets around your iron poor and alpha rich stars. So whether or not there's some sort of population, there's a difference in population statistics here between alpha rich stars and alpha poor stars is an ongoing investigation, and something that I'd love to try and investigate post PhD. And so with the measurements that we have with GALAH DR3, we can determine how much of these planets will likely be confirmed with follow-up radial velocity measurements on the ground. And so what I've been able to do is I've been able to use the Chen-Kipping relationship to convert from radius to mass, and then from the mass to work out the semi-amplitude of the planetary signal here. And there aren't a lot of, you just have to trust me that there aren't a lot of gray dots underneath here. And so there's an interesting space here where there's not a lot of planets that have been discovered here so far. And you can see up here where your stellar V Sun I and what's happening there is that you get the broadening of the lines, which makes the actual precision of the radial velocities just incredibly hard to follow up and confirm mass measurements here, especially with these stars here with rotational velocities greater than, say, 20 to 30 kilometers per second. However, it's not impossible. I'm currently following up an exoplanet at the moment, orbiting around a rapid rotator. It's currently orbiting around a star that has a rotational velocity of almost 30 kilometers a second, but it can be done. And so that paper will come out later this year. So what I just wanted to finish off with today is that to better characterize exoplanets, we need to better characterize the stars. And to be able to better characterize the stars, you can see within this conference here, we need to also better characterize the Milky Way. And there aren't a lot of papers that do this really well, but one that if you really want to get your teeth stuck into this, I would really recommend Carrillo et al. 2020, because that is an awesome paper that combines all three. So this is my too long didn't watch, summarizing my talk, and I'm more than happy to answer any questions that you all have. Thank you so much.
Thank you, Jake. We have time for one question from Jake's talk. A question from Fan Lui. I wonder what's the abundance precision required to estimate the planet structure / composition. Also, are there any elements particularly interesting except for magnesium, silicon, iron, and oxygen?
That is an awesome question. And so Natalie Hinkle and Cayman Unterborn released a paper a couple of years ago to try and actually better understand, okay, what sort of precision do you actually need in your abundances to get down to actually determining the geological composition between different planetary populations. And it is absurd in some cases. I think the precision for, say, aluminium and calcium needs to be beyond 0.0001 dex. And so the stellar community here would just laugh at such an attempt. But there's great work by both Carolyn Dawn and Cayman Unterborn by using just stellar abundances and the stellar abundance errors that we currently have to actually determine the composition. So instead of just going, okay, well, these planets might be silicon rich or might be magnesium rich, they go, okay, the ice sheet might be this many kilometers deep, and its mantle is comprised of these different these types of different compositions, and then your iron core would be this big, and so yeah, it sort of really breaks down that degeneracy, because unfortunately, well, not unfortunately, but if you have one Earth mass and one Earth radii planet, you can have a multitude of different compositions. So that's why you need those stellar abundances there to help out with the composition. But what was the second part of that question? Sorry.
Interesting elements.
Oh, interesting elements. Yeah. So the refractory elements are really what's needed. So your iron, magnesium, silicon, aluminium, calcium, and there's also other interesting elements there as well. I think I've seen a paper about thorium, which is quite interesting in terms of heating of an exoplanet. And yeah, and the carbon and oxygen abundances are also really important. Yeah.